are we doing what we're doing, or why do we want to unit test or integration test? Late testing is a real problem and it's very expensive. So the effort for retesting increases exponentially with the phase in your project. So we need to learn and test earlier. So what we want to achieve is to bring the unit test and especially integration and the system test to the desktop of the developer. With the unit test, that's very easy because it's just software. So it's fast, it's cheap to implement basically. It's really good to automate, but with the integration with the system test, that's much harder to do. So let's compare the two levels or the three levels and talk a little bit about how we can achieve this. One of the biggest problems for embedded system testing or embedded testing is that we have a huge gap in the areas where we actually can test. So let's have a look at the development process for an embedded system. You start, for example, on an evaluation board with your project. You configure your drivers, your hardware-related software components, for example, a motor controller or a battery controller, bus protocols, CAN, LIN, and so on. And on top of that, you have pure software components. You integrate this to an application, and eventually you go to the real control unit, so to the real target where you actually run the project in the real world. So the points we usually test are here. So with a unit test, you can test most software components isolated. The problem with the unit test is that you cannot test everything. So especially the hardware-related software components or drivers and so on, they are really hard to test or not to test with unit tests. Even pure software components, if they have a history, if they have a state, if they have, for example, a motor controller or something like that, it's really hard to test because a unit test just is not well suited for testing this asynchronous behavior. So later in the process, a lot of companies do hill tests or a system test. And the problem with the big hill test or even the system test is they are usually very late in the process. They're very expensive, so they are only repeated every couple of months or weeks, something like that. So a fast response you don't get there. What we do with the mini hill is the hardware-software integration test over the complete development cycle, especially in the early phases. So when you're really coding, you want to integration test your software on the microcontroller, including all the drivers, the motor control, battery control, and so on and so on. So that's what we do, and it needs to be completely automated to be valuable for regression testing and so on. So what do we really want and need? So we want to test what is changed most frequently, and that's your software. That's really good with unit tests because they are easy to do, they are really good to automate, and they test basically a lot of your software. So what you also want is to test every code change of every developer within minutes instead of weeks. No? That's with unit tests, it's not possible to test the lower levels, so you need something else there. You want a full regression test also for unrelated code. So you change something in a module, and at the other end of your application something fails. That's very typically, especially for embedded systems, because you have resource constraints, everything is working in the same memory. So there are a lot of side effects. You might have unwanted interrupts or interrupts that block something else, something like this. And in the end, what you need to enforce tests is continuous integration, full test automation, and you also save a lot of time by using continuous integration. Especially if you have a distributed team, if a lot of developers are working on the same project or even on different projects, on different libraries and so on. And apart from unit test, what you also need is an automated hardware in the loop test, because you have more than software units. If it's pure software, then the unit tests are really good. If it's embedded software with drivers and so on, that's just not sufficient. So you need more than unit tests. Let's have a look at the different test levels and test methods. Let's look at a normal electronic control unit with a microcontroller. You have the software units inside, the drivers, and so on. Then outside the microcontroller, you have the power electronics, sensors, actuators. And in the system, for example, you have a motor, a pump, and a hydraulic system. This would be, for example, a lubrication pump or a hydraulic pump or something like that. And the levels where you usually can test, you don't have to test everything on every level, but a unit test is theoretically just testing one single unit, so one class or one C module. So this would be a unit test. But the software integration test that includes or integrates more than one software unit, you can do also with the unit test tool. So that's the level where you can work completely with software tests. The problem is there might be components you cannot really test with unit tests, or not, at least not very efficient, because they need environment simulation, they have a continuous behavior, closed loop, and so on, and that's really hard to test with the unit tests. So the next level would be the smallest possible hardware in the loop test, and that's where the mini hill comes into place. You take the microcontroller as a black box, so the real microcontroller as it works in your application, including all the drivers and the complete software stack, maybe only the drivers if you want to test only the drivers, but usually the complete application. And at the pins of the microcontroller, you can run a black box test with the mini hill. The next level would be the big hardware in the loop test. For example, including power electronics, simulation for sensors, and so on. So you have a temperature climate chamber or something like that, or even a simulated torque for a motor or something like that. So the last level would be the system test, including everything that's outside your ECU, including a complete system like a motor, pump, and the hydraulic system. The problem is, we have another class of toolings or of methods. Here we have the static code analysis. This helps you on the pure software level. Static code analysis or also reviews are also a static analysis method. So can be very valuable also. And down there, you also have the manual tests. You always can run a manual test, especially in a system test. It's often not automated. So those are manual tests. You get into the car and you drive around the block. The problem is that from the pure software tests down to the system test, the effort increases exponentially. So a software unit test, for example, it's easy to automate with continuous integration. You can run it whenever you change something within minutes. System test, you're driving in the car through the desert in Nevada, Death Valley. That's something you don't do after every software change. Yeah? So those are the two extremes. And what we essentially want to test as much as possible automated. And that's again where the mini hill comes into place. Let's have a closer look at this now. So what are the typical response time for those test levels? With a component test, a unit test, usually you have a reaction time, a response time within minutes. So after every change, you press the button in your IDE and you run the unit test, or the continuous integration runs the unit test. That's really fast. Hardware software integration test usually is not done, so most people don't know how long this takes. A system test simulated with a hardware in the loop test system or a real system test is usually not done very often. Every couple of weeks, maybe every couple of months, depending on the effort you have to put in. And the acceptance test is also on the system test level usually, so it also does not run very often. So speed is the message, because we need a fast response if you want to fix the bug early in the process. If you do not want to have effects down the process, if you detect a problem in the system test, let's say a small software problem or something like that in a system test, that's really expensive. Yeah? We have to rerun the system test. So with a unit test tool, for example, a TESI, you can get response within minutes. Then with a mini-hill, this minimal hardware in the loop test, you also get a response within minutes. If you have longer running tests, make 2 stages. First commit stage, you get a response within minutes, and then later you get a response. Maybe you run the long running robustness test overnight or every couple of hours or over the weekend. So fast response is really crucial to speed up the development and to speed up the development of quality software. Also helps a lot with quality if you are fast. So let's have a look at what you need to test. In the middle, you have the system or component under test. And the test cases are not sufficient. So usually if you have a pure software unit, let's say a class or a C module, you have a unit test. But at the other end, at the lower end of the component you're testing, there are a lot of includes, a lot of function calls, and usually you need to stop them and mock them. So that's what you have to do with a unit test. Unit tests usually are synchronous, and they need stubs and mocks to satisfy the interfaces that are not directly tested, but they are needed to compile or to run the component. The other end is the integration and the system tests. Usually they are asynchronous. You have an asynchronous system. You have states. You have things that are running concurrently. You have motor controls and so on and so on. So they are really asynchronous. So you need asynchronous test cases. And at the lower end, at the interface level, you also need to satisfy the interfaces, but that's not so easy because usually you need a closed or an open loop simulation. For example, to test the motor control system, usually you need a closed loop simulation of the motor, because if the motor is not attached to the system, your system fails. You don't even get to the state where you actually can test something. So that's very important. So that's one of the big differences here between unit and integration and system tests. So you need more than test cases. So what can you do now with the hardware-software integration tests? Since most people are familiar with unit tests, I'm focusing on the hardware-software integration test now. The main goal is not to test, for example, the motor control, so one single component in your system, but integration of such a component with the complete software system, including drivers, electric signals, and so on. So by doing that, you can put your system into almost any state to test it just by changing the environment simulation. This enables automation, speed, and depth in your test process. So let's have a look at an example. So for example, the shutdown path for temperature in a motor control system. We look at the microcontroller as a black box, and we're testing at the pins of the microcontroller. So what I want to know now, whether the temperature, high or low temperature, leads to a shutdown of the motor. So what do? I stimulate the analog signal, electrical signal of the ADC to provide a temperature signal. That's too high, for example. And then internally, in the black box, the events cascade through the system. And what I want to monitor, or what I expect, is that the PWM is off after 100 microseconds, for example, because it might be a safety critical function. So I need to make sure that the PWM is really off after 100 microseconds, and it stays off. And at the other end, for example, I want to know whether the correct CAN message is sent with the right error. Maybe the error could be masked by another error, and then I get the wrong error message. That's all possible. So that's what I want to test. How do we do this? we have a little hardware and software solution to do exactly that. So on the right side, you see the system under test. That's a microcontroller, Cortex M4, for example. So that's your microcontroller in your application with your software. So that's a black box. You can use an evaluation board. You also can put the evaluation board next to the mini hill and connect it directly with those wires. And then we connect the pins of the system under test over the those wire jumpers with the test system. So the blue board here is the mini hill test system. And here that's the microcontroller that actually runs the environment simulations and the test cases. So now we are connected with the pins of the system under test. And now we need to do three things. First of all, we need to connect all the, we need in the software on the left side, we need all the signals we need to test the system. So digital, analog, SPI, all the low level bus protocols and so on, PWM. So everything I need to really simulate and test the environment here. And then I need the environment simulations. That's the next level. So I need a motor simulation or a bus protocol or whatever it is, battery simulation and so on. And on top of that, I can place test cases that try to break the system. Because I have a simulation, environment simulation, I can not only test the happy path, but also the unhappy path, because I can break the system. I can take away a signal, or I can let the motor misbehave, change the direction, insert the wrong temperature or whatever. Yeah? So that's the hardware platform. So essentially here we run a virtual twin of the real system, and by that fooling the control into believing that there's a real system attached. So in order to do this, we need a lot of software. We need the drivers in the system, we need the environment simulation, and we need the test cases. And for that, we have a model-based development approach. It's a component-based system. You can model the structure and the behavior for the environment simulations and for the test cases. From there, we generate C code, we compile it, we flash it to our mini hill board here. We need to run it directly compiled on the mini hill board because it needs to be hard real time. If you have a motor simulation, you need to run this with 20, 30 kilohertz maybe. We have even simulations that need to run much faster. So this needs to be hard real time. And even some test cases might be hard real time. If you want to monitor the reaction of the PWM within 100 microseconds, you need hard real time in the test system. So then we run the tests and we log the tests over a USB interface to the PC or to the continuous integration server. We transform this into diagrams because we as humans understand diagrams much better than text. So for most use cases, we have different views here we generate, and then we learn and we iterate. Either we change the test system or we change the system under test. It's always the same process. So now the next level, that's how we do the integration testing from a technology point of view. So now, why do we want continuous integration? The main focus here is automation. We want to enforce the test. We want to save time, but we also want to make sure that every change is tested. So how does this work? The developer commits their changes to the source code management system. Every change triggers the continuous integration server, in this case, a Jenkins server, for example. The builds are automated, the tests are automated, and potentially also the releases. Please do that. A lot of value in there, even if you do not really release automatically to your customer. But the fact that you can automate the release or that you automate the releases tells you that you can release anytime. Whenever you need something, a bug fix or whatever, you can release it within minutes or hours or something like that. That's important, just as a little side note here. So every change is integrated and tested, and please not nightly, not weekly, continuously, every commit. If it takes too long, make steps. Make 2 steps, short step and a long step stage. So early and often, fail fast. So bugs can be detected and fixed very early, sometimes within minutes. So whatever you test, make sure that you get a fast response. So what does the hardware in the loop look on your desktop now? That's a setup for one project. For example, you have the mini hill board next to your laptop or to desktop. You connect it, you can model the test environment and the simulations and so on, and connect it, trigger the test directly from your laptop. So for continuous integration, you need a little bit different setup. You have a server, and attached to the server, you have all those mini hill boards, for example, in a rack. Now that's a typical setup, in this case with 8 different projects. So it's a meter high, for example. You can put 8 projects with customers that have 20, 30, 40 projects in parallel running on the continuous integration server. It's relatively simple to do. Everything is on command line, what we do, so you can always integrate into any continuous integration server. So every commit is built, tested, and delivered. The tests run, so the hardware in the loop tests run on the mini hill board. So every code change of every developer, doesn't matter where he sits, for every project is tested within minutes. That's always our goal. Let's have a look at the little demo I'm about to show you. In my demo system, I have a TLE, no, I have a STM32 microcontroller, Cortex M4. It runs a BLDC motor control. The motor control generates PWMs and block commutation. They are measured here on that side, on the test system side. Simulated. The simulation generates 3 Hall signals to satisfy the interfaces of the motor control. So it's a real closed loop simulation. So if the motor changes if the motor controller changes the speed, the system follows the simulated system. Then we have a temperature sensor as an analog output. We simulate that one. Can also be a digital interface, whatever it is. Then we have a UART to control the speed for error messages and so on. So that's a pretty typical system we test. Usually there are more IOs, but that's pretty close to a real world system here. On an electrical level, test cases look like that. So that's a log for a logic with a logic analyzer. Usually you don't need that to verify whether it was okay, because it's automatically verified. But just to explain you what we do here, you see here the PWM signals that are generated by the motor control. They are measured, simulated, and then the simulation generates those 3 digital outputs as a simulation for the Hall signals for the motor. That's the UART protocol here. You see the messages that go over the UART. If I go a little bit further away, you see the PWM, you see the Hall signals like the speed changes and so on. Here the UART signals. Then you have the simulated temperature as analog value. Here you see basically the boundary values and the equivalency classes we test here. And here you see that's a pure output of the simulation as an analog output. We put the current speed of the model of the motor model as an analog output. That's easier to understand than those curves here. So, and now we can have a look at concrete test cases, like you want to change the speed over UART. So what happens? The PWM in the system under test gets slower. So the test system gets slower, the simulation follows. You see this here, and that's the speed of the simulation. So the next test case would be a full stop on a motor error, on a temperature error. So here you have a low temperature, it's below, it's an error temperature. Here you have another high temperature test. And what we want to test whether after 100 microseconds, for example, the PWM is set to off, and we wait something like 0.2 seconds to make sure that that it stays off. And then we have here we have a limp home functionality. That's a warning temperature, so the motor just gets slower to recover the system. And here I have after full stop a recovery of the system. So those are typical test cases, and they are completely automated. That's just to show what it looks like on this level. So on my machine, on my local machine, I have the laptop, I have the mini hill board. Here you can see the mini hill board next to my laptop. I developed the simulation and the test models. I commit to a Git source code management system. Every commit triggers the Jenkins server, which also runs locally on my machine. We build, flash, and run the tests, and the results are propagated and displayed as diagrams. Exactly the same process works for the system under test. That's, of course, what we want to do. So every change in the system under test is also committed and triggered and built and tested and so on. So the process is exactly identical for test system development and system under test development. So it's always the same method here. Okay, let's have a look at the little demo. I'm going to show you the development environment. The modeling environment gives you the possibility to model your test system with components. They are hierarchically. So, for example, we can go down here. You can decompose your structure deeply, and so on. And then down here you model the IOs. Most of the components you get out of the box. For example, the analog out adapter here, the port 1, that's exactly this red cable here. So it's an analog output with 3.3 or with 5 volt. Here we have the duty capture unit, motor simulation, Hall generator, and so on. And so those are the IOs. Now that's the simulation level. Simulation level is, for example, the motor temperature translates from degrees Celsius into an analog output. The motor simulation, it's a bit more complex. This can be a state machine. In this case, we modeled it as a state machine. That's also part of the tooling here. So whenever the PWM changes, we remember the duty cycle, we calculate the new speed. That's the new speed calculation. And then over the Hall generator output, that's the port to the Hall generator, we can set the new speed or the new direction. So by that, introducing failure injection and things like that. So that's the modeling you can do directly in the tooling. You can also use, if you have a plant model for the simulation of your, in Simulink, for example, or in C code, you can integrate this directly here into those simulation components. So now we have the IOs and the simulation. The last thing that's missing is the test cases. I said before that we need asynchronous test cases because we have an asynchronous system. So we might want to monitor things in parallel. And for that, we have another behavior language. We could have used state machines. That's what we did at the beginning. But state machines are not very efficient in describing test cases. So we decided to create another language that's also deeply integrated here. That's test language. The test language works with the same interface as the components here. So UART, motor simulation, motor temperature, you can all access this directly in the test cases. So for example, here in a test step, I can communicate with the UART directly, or I can for example, change the motor temperature to 23 degrees and so on. Here you see always what you changed. With the steps, you can create actions and reactions. The reactions can be concurrent. So, for example, in this case, I expect 2 concurrent reactions, and I don't care about the order. In this case, I care about the order. So that's important because you might want to trigger something and wait for 10 or 20 events that happen after the change. So that's how we model the smallest steps here. And on the next level, we want to integrate those steps into sequences. For example, here I have a sequence to test PLC speed. Here are the steps, and you also can integrate steps and sequences into higher level sequences like here. So you can make it as deep as you want. In the end, you integrate everything in a test suite, and that's, for example, the test suite to test the complete motor control. So that's how you model the environment simulation and the test cases. Now I can build the system directly from the graphical user interface, generate the code, and compile it and flash it. I also can use a little graphical user interface we provide to do this. If you just want to run the tests, you don't need the development environment. And now I'm going to I connect with the targets here, so with the mini-hill test system. And while it's testing, I'm pulling a wire. For example, I guess it's UART. I'm starting the test, and I'm pulling. Now you see the test is running. So I'm pulling the UART here. I'm repairing the system again. So now you've seen I triggered some failures here. And in the end, I get the log with, for example, the error here. I can click on the error, and I'm back in the development environment, exactly in the line where the error occurred. So the last thing I wanted to show you is we want a fast reaction. So I'm not using the manual trigger now. The test run is automatically, but the trigger was manual. I changed something and I pushed the button myself. But if somebody else makes a commit, I want this to work as well. So I'm doing a little change in my system under test now. So it's in the same development environment, but now I'm changing the system under test. That's manual C code. And I'm going to into the motor controller. That's just a piece of C code here. So, and I'm going to change the duty cycle. Sorry, I made some experiments here. I'm reverting this. That's all under version control, as you can see. Okay, so now I'm going to change the duty cycle to a fixed of 20%. So this should trigger some kind of error because now the motor is running constantly with 20% of its speed. And now I'm committing this change, name it bug. So I introduced a little bug in the system under test. Now I'm committing this, and I'm immediately switching to the continuous integration interface that runs locally on my machine, but can also, of course, run in on a server. So I'm committing the change here. So let's commit this. Oh, just a second. Commit this change, and now immediately the continuous integration server detects the change, as you can see. And now I'm placing the camera next to it. So the continuous integration server now checks out the new software version, system under test in this case, assembles both projects. If there's nothing to do, nothing is done. Now they are both flashed. Here you can see the LED stopped on my board. Now it's restarted again. Same with the system under test. It's also flashed. And now the test cases are running, and I can have a look at the textual log That's not very interesting. If you need the details, you have the textual log. What's more interesting later is the graphical log. So now the system is really simulating the motor and running all those tests I've shown you before, starting a motor, testing the different speeds and so on. And in the end, it found a problem. So it's unstable, it's yellow. That means at least one test case failed. So last test cases, in this case, the demo integration test, motor control speed, temperature failed. So now I want to see what really happened. So I open the log, it's now on the server, and I see exactly which test case failed. I click and my IDE opens in the right state or in the right step where it actually failed. Okay, that was the little demo. I hope you enjoyed the demo, and if you have any further questions, don't hesitate to contact Hitex, Michael Weiss, or myself at PROTOS, and we can discuss your requirements. And yeah, so that was it from my side.